Okay, lesson 5-6, inverse relations and functions. So with an inverse, one of the first things that you need to understand is that in a table of data, when x turns into y for the inverse, the y needs to turn into the x. So what that means is you basically just have to flip the columns around if it's an inverse. So if these two tables are going to be inverses of each other here, when x was -2, it turned into a 1. The inverse needs to undo that. So when I have a 1, it turns into -2. And when a -1 turns into 4 here, in the inverse, the 4 needs to turn into -1. Inverse just is like it undoes the other one. So 0 turning into 3 means a 3 has to turn into 0. And 1, 1 would just stay the same because since the numbers are identical. All right, so then the next thing is on a graph, how does that look? So you see this little graph over here on the right. Those first yellow dots, a -2, 1 here, and then a -1, 4 up here, and a 0, 3 in there, and a 1, 1 sort of in there. And so if you have those three dots, as opposed to these other three, 1, -2 down here, and I'll give you a hint here. If you keep them, the ones that went together matched up here, it might help us see what we want to see on the next observation. On the 4, -1, that one would match up like way up here with this one. If we go to the 3, 0, that one matched up with this one. And if we go to the 1, 1, it matches up on top of itself. And then the question becomes, well, how are all those related then to the other ones? And if enough observations were asked, or if I checked with enough people, hopefully what you would say is that blue dotted line is the y equals x line, and each of the inverse points are reflections over that. So where this went over there, obviously if it was on itself and it goes over that line, it stays on itself, or at least I hope that's obvious. And this one reflected over here. And let's see, and then this one reflected over the line to go over there. So an inverse graph is always a reflection over the y equals x line. The table, the x and y's columns, always just swap. And then they ask on this one too, if we have x squared, and I have this table already kind of sketched out for you, -1, 1, you've got a parabola here, basically 0, 0, 1, 1, and if you go out here to your 2, 4, and your -2, 4. And then the question on this one becomes, when you reflect it over the y equals x line, what happens there? And so one thing that you have to do with this one if you think about this, -1, 1, this would be 1, -1 here. And if you do this -2, 4, this would be 4, -2 here. So what this one's doing is coming out like that. And then your 1, 1 would still be 1, 1 there, but your 2, 4 would be 4, 2. So this one is going to be sitting right over there. Now the comment over here about the domain restrictions is the fact that if you have an x, like right here, this 2, and it has 2 different y values there, that's not a function. You can't do that because in a function, I have to know, if you tell me an x, I have to know it has to only have one y, so there's like no confusion of what's involved. So in this case, what we do is we take the bottom part of this graph and we take that part off. So if you use the original parabola, so the right arm, if you use this right arm and you go from 0 to infinity for the domain on there, then because of that, you would only have the top part of this parabola and not the bottom. So then if you only keep 1/2 of that, and then you could say it another way then to also kind of emphasize this point. If you go back to your x squared, and we said an inverse is what undoes it, well, what undoes an x squared? And so hopefully you would tell me that the inverse in notation looks like that. The formula that undoes an x squared, that's what this is basically saying, would be the square root, because the square root of x undoes a square. And so all those pieces go together. These are reflecting over the y equals x line. We eliminate the one side so that we don't have this problem with not being a function. And if we had a table of data over here, if you go to your square root and you put in a 0, don't you get a 0? If I put in a 1, I get a 1. And if I put in a 4, I get a 2. For this, my inverse. So all those pieces, we've got the inverse formulas. We've got the inverse tables. We've got the inverse graphs. We mentioned this domain restriction. And for our graph, we said how we reflect over the line. I think we covered it all. All right, let's go ahead and move on. All right, so what's my inverse on this one gonna be? So let me show you a new strategy that I didn't talk about on the last example because I thought you'd just understand that one. So on this one way that they say this, so I think most everybody knows f of x is like your y. So we start out with like y equals square root of x minus 2. For the inverse, a lot of books explain it this way, so I'll say it this way. To me, it's not a big deal if you just do a slight variation of this, but you have your x and y trade places. And now you just do what you need to undo operations until you get y alone. Remember in our table, isn't that what we said for our inverse in our table, that the x and y traded places in the columns? So I just had my x and y's trade places, but then for the inverse, I need to get my y alone and solve for that now to find that formula. So what would I undo here first? I'd square both sides. So now my x squared, this square undid that square root, so I just have my y minus 2. And then lastly, add that 2 over. So my formula ends up being y equals x squared plus 2, and then the notation-wise, that's this f to the negative 1. So it looks like x squared plus 2. I'll show you a method that sometimes I've used with students. Some like it, some don't. They think it doesn't make sense, and that's fine. You don't have to use it. But looking at this formula right here, to find the inverse formula, I write down an x. What do I undo first on that thing? Well, I undo the square root with the squared, so then that's gone. And lastly, what do I do to get x alone? Add a 2. So it took out all of writing all these steps out over here, and then you add on your inverse notation, and you're done. So if you like that, feel free to use that for my class. I think anything you can do to speed it up, I want to help you be better prepared for those high stake, lots of money at stake, SAT, ACT, great scholarships. So by all means, feel free to use that. All right, let's go back to our graphs then, since it's over here. You can make a table of the two and graph the points. I'll go back to, remember we knew that the square root graph looks like that. And this would just be where it's been moved 2 to the right. So what I would do is just take that square root graph, move it over 2 to the right. And that right there is this graph right here. All right, then let's take the next one. Is that not a parabola moved up 2? So a parabola moved up 2 would be like this. Now remember on this one, we can't use both of the arms, so we have to restrict the domain, they call it. So my domain on this one has to be restricted so that it's just 0 to infinity. So it's only the right arm and not the left arm. So then we'll take this part off from there. And then I would ask you again, so does it look as though those two are reflections across the y equals x line? I would argue that it does indeed seem so. So that is all matching up. Take another one. What's the inverse here? Now I'm going to use that other strategy I explained on the last problem where I said I write down my x. Looking at this formula, what do you got to get rid of first to get the x alone? Well, we got to get rid of the plus 5, so I put a minus 5 here, and then think of that as gone. And what would you do next to get x alone? Divide by 2. And so then that's the next thing I would do here. So there's my inverse formula. Now, algebraically, how do you prove these are indeed inverses? That one formula undoes the other. And so what you have to do is you have to show that if I put my f of x into g, remember when we did composite functions? Everything gets undone and all I have left is x. But you can't just do it one way, you gotta also do it the other way because it has to undo in both directions. So let's just see what happens here. First one, take your f formula, this fraction, put it in place of this x, so I gotta multiply by 2, and then add 5 after that. The second one, take your g formula, the 2x plus 5, put it in place of this x, so I add on this minus 5 out here, and put it all over 2. Remember what we said, has to equal x. When it undoes it, forgot to put that out here on this one. All right, what does this 2 that I'm multiplying by do to that dividing by 2? And hopefully you agree that divides out to 1. And then what does minus 5 and this plus 5 end up doing? There's just an x, that's good. How about over here? What does this plus 5 and minus 5 do to each other? And then 2x divided by 2, what's that do? And so that's how you prove algebraically, prove, when it says prove, that's what you have to do to show that indeed they are inverses of each other. All right, are these inverses? So we're going to do that same thing we did on the last problem. We're going to put this one in place of this x and see if it undoes everything. So all we have left is x. And then we're going to flip it around the other way, and we're going to take this one and put it in place of that x and see if it undoes everything to end up with just x. So if I'm putting the pink one over here into the blue one, that's like I'm going to put f of x into the g of x. Otherwise in dot notation looks like that from what we said earlier. And so what does that look like in a formula? So the f of x in place of this x into the square root. So I've got a square root, I've got an x squared plus 5, and then I've got a minus 5 sitting out here. And then I would argue that nothing cancels out. This does not cancel out. This minus 5 out here does not cancel out with that 5 unless it was underneath. So these are not inverses. The only way that they would have been is if everything canceled out and they had an x when I was done. I could still do the other side just to show you. If I put the g formula into x, so I'm going to take this square root of x and then a minus 5. I'm going to put it in place of this x over here. So this whole thing gets squared. The whole thing gets squared because of this squared. And then I have this plus 5 afterwards. So this one, you could work this out, but again, this is not going to simplify down to just an x because of this squared. You got to FOIL this out, this whole thing. and then a +5. And so this is going to have some square roots left in it, some other stuff. So this one is not, these are not inverses of each other. All right, so I've got a volume of a sphere, 4/3 pi r cubed, and we're supposed to rearrange that equation to get r alone. So that would be like, I'm going to sort of like doing an inverse. I'm undoing some operations. So how do I get the r alone? So it's like you say, area of the sphere equals 4/3 pi r cubed, and we want to get r alone. Well, one of the things I like to do is just one step at a time. So how do I get rid of dividing by 3? Multiply by the 3. So then those are gone. How do I get rid of this 4 times pi? Well, I would divide the whole thing by that 4 pi. And lastly, then, how do you undo this r cubed? With a big old cubed root. And so then I'd have my r all alone. If somebody doesn't like me showing it with all that shorthand shortcut and needs every step written out, let's see how that looks. So again, I've got my 4/3, my area equals this, 4/3 pi r cubed. First, undo the dividing by 3. So then I have 3a equals 4 times pi times r cubed. Trying to get r alone, remember what our goal is here. Divide by the 4 and the pi to get the r cubed by itself at least. So then I've got my running out of string here. 3 times the area over 4 times the pi, and it ends up equaling my r cubed. And how do you undo an r cubed with a cube root? So all the same steps, except over here I left off my cube on the cube root. Wrote it in the step above. So that would be my inverse, or just rearranging. Then it says, well, what if you have a volume? Oh my goodness, that whole time I was saying the wrong word. This is volume, not area. I know better than that. So where I wrote this A, this really should be a V for volume. Take that out of there. Whoops, sorry about that, everybody. So this was the volume. When they started talking about volume in that problem, I realized I had a bit of a problem. Okay, so how they go on and they say, well, if you have 4.5 for your volume, then what was the radius? So all you have to do is put your 4.5 in place of this volume and do that calculation, and bada boom, bada bing, you got it. So 3 times 4.5 all over that 4 pi would give us the answer to that question. All right, and I think that wraps up that lesson. So good luck there.